Yes, good afternoon. I'm Dennis Brown, otherwise known as VK6FADF, Foundation Licence Amateur, and I've been licensed since March-ish last year. One of these days, when time permits, I'm hoping to upgrade to a standard and/or advanced call. I'm joined today by Lee Thompson, who's been licensed since the 1960 and has been working with magnetic loop antennas over the last 10 years or so. This presentation should be given ideally by Alan Hutima, VK6MST. Alan is currently enjoying the climbs of Sydney on his boat, half his luck. Because Alan and accidentally myself got involved with experimentation with magnetic loop antennas, and on my side of things, wisely or not, I contributed the notion of using an Arduino device to control the tuning of the magnetic loop. So I think at this stage of the game, since the bulk of the presentation will be focused on the mag loop, and there's not that much smarts involved in the Arduino side, I'd like to hand over to Lee. Perhaps before doing so though, how many in the audience are licensed amateurs? Probably quite a few. Yeah, okay, that's great. How many have been using magnetic loops? Or yes, 1, 2, 3, excellent. Okay, if I can hand over now to Lee, please.
Thank you. Can you hear me okay?
Stand up.
Yep, good. I've been playing around with magnetic loops for approximately 10 years, I suppose, and you wonder how you could do very much with a square piece of pipe or a round piece of pipe. But the problem we're facing today is that we don't have any room to put up antennas, and anybody that's got a small backyard has a problem. And I've been working on these things. I've got a little demo one here.
Lee, can you put your microphone a bit higher?
A bit higher. How's that? Is that okay?
Much better.
Okay. I just put this little mag loop together to show you what a magnetic loop is. It's a square piece of, this one is a square piece of 1/2-inch copper tube using elbows. At the top we've got,
Take the controllers down there, or just press the space bar.
I'll just go up to the, yep, that'll do. At the top we've got a capacitor, and at the bottom we've got a matching transformer on this one, and that matches it to 50 ohm output. The loop works in such a way that the resistance has got to be very low, and 0.1 of an ohm is what you sort of need to strive for to get a loop to work properly. If you just screw it together with screws or make it out of a bit of coax or something, you're introducing big losses. So you need to have a good solid design. The capacitor at the top is another place for big losses, and if you don't have a very well designed capacitor, you'll lose half your signal in the capacitor. It ultimately should be made of copper, and it should be the plates you use, only the plates, never use the wiper, because the losses are great there. Now, at the bottom, you've got a current point. It's current down here. You can grab hold of it down here quite safely. If you come up here and grab hold of it, you're going to find out you've got a problem. At about 10 watts, you've got something like 1500 volts at the top here. And so you've got to keep away from it. For 100 watts, you need to stay about 3 meters away. So when you get a little bit higher power, then you've got to get further away. I've been playing around with them. I'm still alive, but I don't. It's all only theory at this stage as to really how far you should be away. Can we just go to the next slide? Oh, okay. Right. Yeah. Yep. This is a magnetic loop made of 50 mil copper tube. It's got a vacuum capacitor at the top, and it has a tuning range from 3.5 megs through to 18 megs. And it will handle 200 watts. On 80 metres, you can transmit, and most people don't know what sort of antenna you're using. Now, the advantage of the mag loop, even though it's considered an inefficient radiator, is that most people can't put up an 80 metre dipole at the full height. So you want to get it up at 150 feet or something to get maximum efficiency for a dipole on 80 metres, whereas this works quite fine sitting on the ground here. In actual fact, that's below ground level. That's the main ground level up there. And I can work on that little 817 into Albany with 5 and 7 reports on 80 metres. Now that's a very efficient loop. That's a half Faraday shield there, forming the loop, which is 5% of the total diameter. And all the joints are all welded. And this is where it's going to come in handy, controlling the loop, because if you can't, you've got to go outside and adjust it every time. And it'd be nice to have it so that it's tucked away somewhere and you can remotely control it. That's where the big plus is going to be. The loop itself is directional to a degree. You can rotate it. With this little loop, just playing around with it, you can put it on the ground and you've got a 5 and 7 signal, and you can lift it up in the air and you've still got a 5 and 7 signal. So in theory, you could just have the two sides attached to a metal roof, but you've still got your coupling, which you've got to then you'd make a gamma match for it, and it'll still work. If it's on the ground, you can bring it over to about 45 degrees and it'll still function quite nicely. The impedance match is 1-to-1, quite easy to achieve 1-to-1, and you don't need to worry about TVI, because the Q is very high, as you know. It's an extremely high Q circuit. You can have it sitting right beside a TV. Don't know about the new digital ones, but no problems. And it's a very quiet antenna. This little antenna here, with a bit of jiggery pokery, works from 7 megs up to 30 megs if you just as a receive antenna, and it's really good, very quiet. I had it working this morning, sitting on the floor on 40 metres, listening to the little guys around, no noise. So it's something that we should all have a play with, and it doesn't cost very much. You can go to Bunnings and get 4 pieces of 1.5 metre lengths. If you put the 4 together and put a capacitor and make up a little matching device at the bottom, you've got an antenna that'll work well on 80 metres and 40 metres and 20 metres. You have to have just under a quarter wavelength on the highest frequency you want to use it on. So if you wanted to use it on 40 metres, you'd make it about 16 feet, be okay. It'll work well. So that's basically the loop. Would you like to have a demo of how it works, or put it on? Huh? It won't work very well in here, I can tell you that. Very good for portable use, take away with you. You know, if you're travelling somewhere. I'll stick it on here. If you like to just switch that on, we've just got a little signal we can put into it.
What band do you want on?
I think it's on 24, isn't it?
It's on 12.
Huh?
On 12?
Yeah, that's 24.
Yeah. Not a band I'm allowed, obviously.
Yeah, hang on.
Not familiar with the megahertz conversion.
Hear that? Now, hear it working on the ground.
So that turned off.
Yeah. Yep. I think that's putting out about, what is it?
Minus 33 dBm.
Yeah. 50 microvolts. But you can see the directivity is there a bit. If you go into the horizontal plane, I can't do that without holding onto it really. You've got to go a quarter wavelength above the ground at least then on the band you want to listen to. So. And if you change frequency, you change the capacitance and you're on the other band. So. I think in the next 10 years, we won't be able to put up HF antennas. It'll be something of the past. And we're going to be stuck with something like this. It's not the ultimate, but it's a very good substitute. And if you're in the marine business, very good antenna to have, even as an emergency antenna. So you could make that tune to the emergency HF frequencies without any problem. You could actually have it fixed tuned for emergency use. Industrially, there's a very big market for the mag loop, and in Africa, they're looking at magnetic loops in a big way because they want to put them on top of buildings for security reasons. They don't want to have big wires, but they still don't have the communication facilities that we've got here in Australia. And HF is still used widely. So, yeah. This loop here is the same as that one. I'll just go to the next one. That's a Japanese designed antenna. I don't want to steal your thunder. Do you want this? That's a Japanese designed one. The shape is something that they're playing around with, thinking that they might get a bit more horizontal polarization out of it, but in actual fact it's a donut pattern. So it doesn't really matter about the shape as much as you might think. If he turned it the other way around so it was vertical, he might get a bit more vertical polarization in it. For DX, it might even be better if he'd gone vertical with that. The little bit of playing around I've done with them, I've got a vertical one, and it does appear to work that way. This one here, this is a 4-foot square with 1.5 inch copper tube, and it's got a gamma match on it, and the capacitor at the top is a copper capacitor. Once again, it's just feeding it's not using the wiper, and that'll handle 200 watts on all bands up to, that one goes to 18 megs as well, yeah, and down to 80 meters. So that's very good for weather. The one previously to that slide with the gamma match, it's not as good at weather protection as the as the other one. Where am I going here? Yeah, this is on a boat. I can't speak. I can't speak, but I'm sure they work really well. It's a neat little one on a yacht. So is that on a yacht?
Yes, that's on Alan's. I think it's on Alan's boat.
Yeah.
It's Alan's first effort. He called it the fast loop because his first call sign was VK6 FAST.
Okay.
And he used that to talk on to the local repeater
Yeah.
as a test.
The capacitors are important. The vacuum cap is very good at handling very high power, high voltages. The only drawback with the vacuum cap is it's a little bit like having an egg mounted on top of your antenna, and you can't have any accidents of any kind, otherwise you break the capacitor. I made I made that loop that you saw back there, the copper one, and I had a 3000 vacuum cap on top of it and transmitted on 160 meters with it. and it was so sharp that my audio was compressed. But it did actually work, and probably had a range of about 100 k's with it. So this is really the best method. This is the butterfly capacitor.
Just sitting there, just in front there.
Where is it? Ah, yeah. The butterfly capacitor, this is a, Dave will tell you more about this, but it's a butterfly capacitor, and the advantage of that is that it actually provides a balance to the loop. It's better than the vacuum cap in that the signal doesn't get skewed. So if you can get yourself a butterfly capacitor or make one, that's the way to go.
So that capacitor was built by Alan on his CNC. It's actually my capacitor.
Yeah, I wasn't going to steal the thunder.
Okay, right.
So, yeah, so that is a really good way to go. And if you do use a vacuum cap, you have to have a choke on your output into the 50 ohm output to stop it being unbalanced. So there are lots of things about loops. You think it's just the 4 pieces of pipe or a round circle and there's not much in it. There's a lot in it, and it's all Ohm's law, and it's all about losses. So there's an example of a match, 50 ohms at 1:1, and it's pretty easy to achieve that. It's quite easy. The little transformer on that one there, I use that same transformer on all size loops. It'll work on any loop. But the gamma match, if you're making something permanent, the gamma match is probably the best way to go. That's an example. I won't go any further than this. I think I'll let Dave take over from here. But I hope you found that a bit interesting anyway. Thank you.
Yep, thanks very much, Lee. I think that's provided a good grounding in the magnetic loop and some of the bits and pieces that go with it. To give some indication, this is that vacuum variable capacitor there, so you can get an idea of the physical size of the beast. This one has suffered a slight mishap in that the vacuum is no longer present, but we're hoping that some kind folks here at UWA Physics Department might be able to reinstate it. It's notable that there's some contamination, there's some oxidation already taking place on the on some of the elements within. And as I was walking up here from my base at QE2, I was musing at the fact that there's no getter. You know, those of us who know about valves, and that will be everybody here, I would hope, will realise that there's usually a bit of metallisation inside the envelope, which I think is magnesium or something of that nature, which after the valve is evacuated, gets fired so that it will suck out the remaining sort of oxygen molecules within, sorry?
Nitrogen too. I can't remember what the element is.
Yeah. I should remember it because it sort of hails from my era. But anyway, it's a nice piece of goods. I think Alan got this one from the Ukraine on eBay, you know, the universal supplier. The butterfly capacitor, as Onno's mentioned, this is one that Alan made for Onno. It could be made out of copper plate, which Lee has mentioned it would be better in terms of losses. It has two advantages. First of all, its balance from an operational point of view, and also it's a lower torque required to actually turn this little guy, so you can use a lighter motor. In addition, perhaps a third advantage is that it doesn't matter how far and how often you go over centre, because there is no limit. These guys, on the other hand, and this is where the Arduino controller came into play, these of course have a defined limit, and if you exceed the limit, bad things happen, and it's not the sort of thing that you want to replace too frequently. More on the physicality. This is Alan's implementation, sort of phase 1, used to drive that. Behind here we can see a couple of limit switches, just ordinary single pole limit switches. The idea being that you drive the stepper motor until one or other of the limits is reached, and hopefully it will step no more. And this is the cover for the cover and mounting. These yellow pieces and this piece here have come off Alan's son's 3D printer, and I expect that as 3D printers become more economical, I see a few sort of heads nodding, as 3D printers become more economical, I expect that there'll be a few of these and similar projects being seen around the traps. That was an earlier illustration of Alan's design. It predates the 3D printing. The yellow and red buttons there is a 3D printed cover which conceals an Arduino shield, an LCD shield. And there are the bits and bobs. Okay, so rather than turn my back to you, the important points as far as the control for the mag loop antenna is concerned is that you need to maintain a certain distance from the beast, not only because of the high voltages that can be involved as you start to feed more power into it, but also you get capacitive effects from the body, so you really want to maintain some distance from it. Alan originally used a geared head DC motor and even went to the extent of using pulse width modulation control, but found that principally as a result of the high torque that you needed to start moving this beast, that was not particularly satisfactory. So somehow or other we conceived the idea of using stepper motor control, and we then looked around for some means of controlling the beast. Settled on the Arduino, but of course it could be anything. It could be a dedicated microcontroller chip, Beagle, you name it. The important point is isolation from your radio and high voltage fields, limit switches if you're going to use a vacuum variable capacitor. The Arduino and its display are located in your shack, and well, he's using Cat5 cable, but whatever happens to be available to provide the link. The stepper motor is, in this particular design, it's a 7.5 degree 12 volt bipolar. It's driven from a little H-bridge, L298 type chip. You can get these things off of eBay for sub $5 these days. Limit switches are normally closed. The reason behind that decision was that if any open circuits occurred in the circuitry, that the limit condition would then be sensed and power would be shut down to the stepper, basically just to protect the rather expensive variable capacitor, and the 3D printed implementation for the base and so forth. In the shack, using an Uno R3, we are rapidly running out of I/O pins though, so maybe a Mega, an Arduino Mega is next in our investigations. An LCD button shield, just the standard design using the, again, off of eBay you can see dozens of these things. There is one that I'll mention later on by Adafruit, which might be actually better for this particular application. 3D printed cover. Where we're hoping to take this is, because at the moment it just has manual control. You've got high and low slew speeds, slew rates, so you can cover the band, and single stepping, so you can fine tune. Because the bandwidth, as I think Lee might have mentioned, is very, very sharp indeed. And you want to achieve that precision. In progress, what we're hoping to achieve is to store a table of values of steps from a calibration position to a known operating frequency. So instead of having to keep watching your SWR and so on moving through the band, you can get within ballpark. And then subsequent to that, once we achieve that, we'd like to add in some SWR measurement as well, and a control loop so that we can actually get in there and fine-tune the thing. The software design philosophy was to be fail-safe. In other words, the limit switches are closed to ground. If an open circuit occurs, you've got the limit condition and you disable power. Slew rates, as I say, you've got a high slew rate and a low slew rate because of the criticality of the tuning. In progress, there'll be a calibration feature where we'll step the system to one end of its range and define that, and then we'll store some values into a table. Because we're running out of I/O pins, as you'll see in a moment, controlling an SD card or something similar is something that we have yet to address, and maybe that'll be addressed in one of the mini conferences if I can get along to one tomorrow as well. The design philosophy of the software, fairly standard stuff. I'm almost embarrassed to talk about it in that regards, but you've got constants and definitions, so you don't have to make changes throughout your program in an ugly way. There's a setup routine in the usual Arduino fashion to set up your parameters. And the main loop then has really nothing much more to do than sense the push buttons, find out what you want to do, activate the stepper in the appropriate directions, and of course keep an eye out for those limit switches. In terms of the Arduino itself, for those who, I presume everybody here knows Arduinos in one shape or form? Yeah, otherwise you wouldn't be here. Okay, as you'll know, you've got some analog pins and you've got some digital pins. For this particular design, we've reserved analog pin 0 for the LCD cum button shield. It just uses the voltage divider to sense which button you've pushed, if any. Unfortunately, the LCD shield is a bit greedy on digital pins, but therein lies a tale. Analog pin 1 we're going to reserve for the SWR sensing. That's a work in progress. And analog pins 2 through 5, because we became rather poor in digital I/O, we've been repurposed as digital outputs to drive the stepper. On the digital side, we've reserved 0 and 1 for serial I/O, not that we're actually using it in this particular context. 2 and 3 are the pins that we've chosen to be our limit switch sensors. 4 through 10 are grabbed by the LCD shield. And this is where, possibly if you were revisiting this project, you might use the Adafruit design, which I understand uses fewer digital pins. In fact, I think the Adafruit, correct me if I'm wrong, but I think the Adafruit interfaces serially. So, you'll give yourself a bit of a favour there. We're using pin 11 to control the H-bridge enable line, because of course if you leave power statically on this motor for any length of time, you'll warm up the motor unnecessarily. Pin 12 has been reserved at the moment for potentially for SD card control, so we can store our table of values. And 13 remains available as just as the onboard LED driver, not that we're using that for anything sensible at the moment either. Where we're going with this is, as I mentioned, the stored table of values, so that we can work from a known calibration point and get reasonably quickly and automatically to a known defined location. Stepper will be manually driven to resonance, and we'll be able to record the values and store them in our table. Fine-tuning using SWR is something that is on our wish list. As yet, it's a pipe dream, but we think it's achievable, and some nodding of heads indicates that could be so. I would emphasise that this is something we haven't actually gone out and researched really, perhaps we should have done, what others have done. We've basically brought this up from first principles. I have a sneaky feeling that it probably aligns with similar projects that others have done, in which case that's good. We're either all right or we're all not. We'll need an anti-hunting algorithm of some sort so that we're not continuously hunting around for our resonant point. This slide is probably completely useless given the current context, but for those who are not yet radio amateurs, please consider joining the fraternity. You can jump in at a variety of levels. I have the foundation license, which limits me to a range of bands, but it doesn't limit me to experimenting with antennas, and that's something that is a fairly, or transmission lines, which is something that's a fairly popular topic among amateurs of any licensed grade. Don't be threatened by the fact that you might need to know Morse code these days, because you don't. So the rules have been relaxed a bit. And beg your pardon?
It's handy though.
It's handy though. I am learning it, thanks to Ono and a group of us who meet of a Saturday morning in something called F-Troop for the foundation licensees and returning hams. Everybody's welcome. I became aware of something called the Koch method, or Koch method, which is one of a number of interesting methods for acquiring a familiarity with Morse code, and I think I've got a couple of letters so far. I've been a bit slack. So anyway, for those who aren't yet radio amateurs, please consider joining the fraternity. And I think on that note, can we have any questions, which I may not be able to answer, but hopefully Lee will. Sir?
Given you've got an 817 sitting there with a really nice CAD interface.
Beg your pardon?
Given you've got an 817 sitting there, FTA.
Ah, yes.
With a really nice CAD interface, so it's constantly telling things what your current frequency is. Why not just grab that serial data as well and have it thrown over your lookup table?
Yes, that could be good too. Yeah. Yeah.
It's not as scary as it actually is.
Mm-hmm. Yeah, that could be a nice thought. Thank you for that. Up the back there. This particular gadget? Ah.
You keep going.
Yeah.
I'm just gonna...
Sorry, the question is what sort of mountings were used for the loop itself? In Alan's case, he's using dry hardwood. Yep. But in some cases, the loop has been, I think he had one out of 20 odd millimetre aluminium tubing, which was pretty much freestanding. It was bolted onto the butterfly cap. There was an illustration there earlier, which I can't access at the moment, but it's okay. The loops that Lee has been producing are largely of, I think, the freestanding design because of the rigidity of the construction.
I'd just like to say that when you're controlling the loop, any cables that come down from that capacitor at the top won't affect the performance of the loop. So you can have a piece of wire coming down virtually right on it and it won't affect its performance. So it's a bit of handy information.
And that's because of the radiation pattern of the loop. Yeah, fair enough. The Japanese design, that oval design, you may have noticed, if we sort of get back to it, I'm not sure if we will. No, that's okay. But anyway, for those who may have seen, it had a couple of additional struts in it as well. And the idea there, they were experimenting with multi-band. So you had an inner loop, which was relatively small, and an outer loop, where hopefully the lower frequencies would ignore the vertical struts. And part of the reason, believe it or not, for the squashed oval shape was so they could fit it in their car. This was a group of amateurs who, somewhere in Japan, who wanted to go a little bit portable, and they couldn't fit the full-size thing, so they squashed it. And as Lee has pointed out, that's not a bad thing. It just alters the radiation pattern a little bit, but you still manage to get the signals out. Yeah.
Jim Tregella's figure by TR published a bunch of stuff in AR about loops.
Mm-hmm.
And on our local technical net, he's been talking about the automated, or the ATU that he's been building for this using similar sort of ideas.
Mm-hmm.
And he's got a
Windbridge.
Or a Johnson method detecting SWR. I can't find it on his website.
Okay.
He hasn't put anything up there yet, but there's a bunch of people who are doing that SWR.
Excellent.
Specifically for the loop.
Excellent.
Stuff. So
I've seen two designs. One of them actually has a phase detector as well, so you can work out which direction to turn the capacitor.
yeah.
Okay.
Johnson, I think.
Right, okay.
There's a lot of stuff going on with that at the moment. In the LFMS
Mm-hmm.
circuits.
What you've got here in screwdriver terms is called a turns, effectively called a turns counter. And that's quite a bit behind that, but that's process for.
Sorry, I can't quite.
What you've designed here
Yes.
in screwdriver terms is often called a turns counter.
Mm-hmm.
And it's a good first step approach.
Yep, yeah, and really that's what we're presenting here. We're presenting basically our plain vanilla design, capable of all sorts of, tweaking and tizzying up, I guess, along the way. And if it's of use to people, and obviously there's a bit of interest in magnetic loops generally in the fraternity. If we're able to contribute something, then that's really good, and we can certainly learn along the way. Yeah. So.
Just interested in what the sensitivity is like compared to say a quarter wave or something like that.
That I can't answer directly. Alan or Lee, because I'm.
If you've got a quarter wave vertical and it's got 4 ground radials on it, the magnetic loop will be better
Okay. Even though it's physically small.
because it's surrounding the end and it radiates. One of the things that I forgot to tell you, I should have, if you've got a loop that's got a 60 mil diameter and you say, well, I'd like to go to 100 mil diameter, the voltage on the capacitor at the top increases dramatically. So where you might have got a load of 5 kV, you'll probably need 10 kV when you go to 100. That would be the ultimate. 1.2 metres, 100 mil. I'm still trying to find someone that can bend the top of the tube. Really good.
Yeah, I'm not an amateur, so I was more interested in the receive side than the.
You get away with something like that.
Yeah.
Mm.
But being physically small is brilliant, really.
Well, that will
Mm.
the data modes on 24 megs is beautiful.
Mm. Mm.
Just sitting on the floor.
And since you're interested in reception mode, transmogrify into one of those, I hope, because I also have one of those little SDR type dongles, and and a growth area. There was one thing I was thinking of, but it's forgotten, so it's probably about time. I think I'm encroaching on the time. Thanks very much for Lee. This, as I say, was really Alan's presentation. I hope that we have done it justice. I know that Lee certainly has from his perspective, and I hope that the Arduino side of things has been, while simplistic, at least a reasonable intro to some of the things that you can do with these. I've also used an Arduino in a VHF beacon controller, because I'm a member of the WA VHF group, which maintains a range of terrestrial VHF beacons. So we've got a little beacon controller going in one of these things, a few other bits and bobs. So thank you very much for your time, and thanks to Lee.
So next we were going to have a few lightning presentations. The first person's Mike Bork, if he's here.